Okay, I'm going to go ahead and get started. It looks like we've got quite a few people in attendance. So I'm going to start off just by introducing myself. I'm Alicia Frame. I'm the lead data scientist at Neo4j. I work on the product team. So what my role is I work with our product engineering team to develop the graph algorithms library. I work with early adopter customers to figure out how they can use graphs for data science use cases in production and take kind of their feedback and experiences back to improving our product roadmap. And then I work with scoping what our long-term roadmap is and where we're going to do more data science with Neo4j. I have worked in data science for the last 8 years, mostly in the life sciences sector, and I'm super excited about using graphs for machine learning. And so just to start us off, I really like to kind of have the one slide that if you zone out for the rest of the entire presentation, this one kind of drives the message home. So this is my TLDR slide. Why should you use graphs for data science? It's a pretty easy answer. You should use graphs when context matters. So there's like the old aphorism of, it's not what you know, it's who you know. And the example we like to give is to talk about, maybe how did you get your last job? Was it based on where you went to university or the specific degree you had or the number of years of experience at awesome company? Or was it influenced by you had a mentor who helped you build your skills in a specific area, or your college roommate introduced you to someone who already worked at that company who could get you up to speed more quickly, or you had a friend who scheduled an informational interview for you, or your old boss made an introduction. Those are all examples of when relationships are the key determinant of an outcome. So to sum up, when do we use graphs? It's when relationships matter. A nice kind of less hand-wavy example that I like to share is when you talk about figuring out who's going to smoke or who's most at risk for being a smoker. It was a big study, it's fairly famous, where they tried to predict what factors predict if someone is going to smoke or not. And they looked at kind of standard data science approach, right? I'm going to go figure out, what is someone's demographic data? How old are they? Where are they from? How much money do they make? What do they do? What's their ethnicity, right? And they actually found out that those were all informative, but the single biggest predictor was, in fact, whether or not they had a friend who smoked. So again, this is an example of relationships can sometimes be the most predictive factors for a model. And using a graph makes it much easier and more straightforward to pull those relationships into the modeling pipeline and frameworks that you're already familiar with. So when we talk about what can I use graph data science for, these are just 8 examples. You can, if you want to have fun later on, you can say, how do you use graph science for X? These are 8 examples that we've run across kind of in our early adopters program, in the literature from customers that capture kind of how broad the use cases are. This is not a niche solution. So if you start from financial services, how can you use graphs for data science? Fraud detection is something we talk a lot about at Neo4j. So I have a transactional graph of who's interacting with who's buying which services, and I want to use the graph to find out what patterns look unusual. Can I find money laundering rings? Can I find someone with more account transactions than I would expect them to have? Can I find people who interact more frequently with each other than they should? And then can I put those into my predictive models? And we'll talk about this later on. Drug discovery is another example. This is sort of what my background is. And if you think about biology and chemistry, these are all really network and systems based, right? You have genes interacting with chemicals and diseases. You have protein-protein interaction networks. So you can use graphs to improve your ability to identify drug targets, so genes that you want to treat with a chemical, or you can represent chemicals as graphs. And there's an awesome talk from the RDKit folks later today around this exact topic. And then you can also talk about recommendations. So graphs have been really popular in the recommendation space for quite a while, but mostly in the context of collaborative filtering. So people who bought this item also bought these items. Can I filter my graph of purchases and find, co-purchase data? The way you can use graphs for data science here is, let's say you have a model where you're predicting what should this person buy next. I want to predict the link between a person and an item. You can use graph-based features or graph embeddings to characterize what transactions look like and better make a more precise recommendation based on your total graph topology. When we talk about customer segmentation, this can be related to recommendations. Historically, you'd think about, okay, I have tabular data. This is like that smoker example, right? I want to break it down into people of a specific gender, race, age group in a specific location. And maybe that's informative. But what you can do instead, if you have a graph of interactions or co-purchases or who's interacted with which products, you can break it down based on who interacts with whom more frequently. So instead of saying, I want to find a white female who lives in Brooklyn, I could go in and say, I want to find a group of people who interact frequently with each other. And they are more likely to have more in common than saying, you know, these demographic groups interact with each other. So this is super powerful. Cybersecurity is a really natural fit for graph data science. We talk about network security, right? So it's really easy to represent your network as a graph. It's naturally a graph. And what you're looking for there is what patterns are unusual. Where are the outliers? I know what a secure or like safe graph looks like. I want to know when there's been a network incursion. So I can use a graph algorithm to describe what my normal network looks like. And I can train a model to predict when something is outside the range of normal. Churn prediction is another one we're going to talk about a little more in depth later on with a real world example. But the idea behind churn prediction is I have a service. Maybe it's a telco, maybe it's some kind of subscription, and I want to understand who's going to leave next. You can use graph-based features. So have any of my friends left the network? Who's the most influential person I'm associated with, and are they still on the network? And companies like Huawei have actually used this. There's a great publication from a few years ago where they found things like when someone with a very high page rank leaves the telco network, their connections are more likely to leave. Search and MDM is really where a lot of this graph data science and network science applications in production or in industry really started. So I just mentioned PageRank. It's called PageRank because of Larry Page. It's from Google, right? Graph algorithms are what powered our ability to really take off with search on the internet. They're very powerful for saying, I have a large graph. I need to sift through it and figure out what's most important. And then the last category here really shifts gears quite a bit. We talk about predictive maintenance. So this is more closer to like the supply chain and operations research sector. So if I can represent my supply chain, or let's say my manufacturing dependencies as a graph, you can find which nodes are the ones where if that node fails, your entire network goes down. Or you can find out what is the flow across this graph and where is there an unusually high level of flow, so I proactively maintain that aspect. So these are just kind of 8 high-level examples. We're going to go way more in depth later on, but the idea is, how do I use graphs for data science and what do I use them for? I can use them whenever context matters, and that's not set to a specific industry. And the basic idea here is when we talk about graphs and data science, we're not saying throw out everything you've done. We have this crazy new thing we want you to do instead. The bottom line is that graphs let you make more accurate predictions with the data that you already have. So this schema is kind of nice. I have my rows and columns on the left-hand side that most companies with a data science team, there's already a machine learning pipeline in place where you have predictive features, you're training a model for some predictive output, you know what you're doing. What we're saying is with a graph, you can create new features, feature engineering, that you can add to this pipeline that you already have and make better predictions. So that's like your churn prediction example. So I already have information like how long has this person been with this service? And now I want to add in, has anyone in their network left this service? So it's just adding better data in to make better predictions. And the other piece that graphs let you get at that I think we don't want to brush over is sometimes when you have your data in a graph, you can make a new type of prediction. So I mentioned with recommendations, link prediction, right? So if I want to predict links forming in a data set, I need to have a graph so I have an explicit representation of those links. So graphs are great because you can both make better predictions with the data you already have, as well as predict new things. And in case you're listening to this and you're like, this is just marketing talk, Neo4j is making this up. Who's ever heard of graphs and data science? I like to have this slide in to say, no, this isn't just us. This is actually kind of in the data science, AI, machine learning space. There's really a general consensus that graphs are really powerful. So instead of forcing everything into rows and columns, using graphs gives you an ability to generalize about the structure of your data in a way that kind of standard approaches just don't have. And Google and DeepMind published a really good paper on this in November 2018, basically a position paper saying, here's a new framework for modeling, use a graph neural network, it's much more predictive. But what was really interesting in their paper was they said the biggest hurdle wasn't the framework or the technology. They said it was, where do the graphs come from that these networks can operate over? And what's really cool for me working at Neo4j is we're a graph database company. We've got the graphs. So what we're doing here is we're bringing the data science to the graphs to give our users a better ability to kind of generalize and make more accurate predictions. And sometimes I feel like this talk can be really high level. You're listening to me and you're like, she's saying we can do amazing things, but what does this mean in practice? So I like to have this slide to just pull back and say, how do I actually do this? We will revisit this as we walk through specific examples, but the general framing when we talk about using Neo4j and using graphs to build machine learning models is you're starting from your different data sources. Maybe it's already a Neo4j graph. Maybe you have data in Spark or SQL or CSVs. You pull that data together and you unify it in Neo4j. And then once you're in Neo4j, you can do graph transactions and graph analytics. So in the graph analytics space, you can start building features either by hand using Cypher queries or with the graph algorithms, basically creating new columns of predictors for that tabular data. And then you can export that into the space where you're already building predictive models. So this fits into the pipeline you already have. We're not saying start again, throw everything out. We're saying this is a tool in your toolbox that lets you make better predictions. And so one thing that we're pretty excited about, and if anyone is attending the Spark Summit in Amsterdam next week, I will be there along with several members of my team. You should check out our awesome talks. We'd like to talk about Spark and Neo4j and how you can put those together. So Spark is super powerful in terms of data unification and data pipelining. Spark 3.0 will have Cypher 9 available. So you can run Cypher and you can project your tabular data into a graph format. And you can create a non-persistent graph. Once you've figured out how do I reshape my data into a graph, do I have a graph problem, you can move into Neo4j just like I talked about. So you can store your graph, you can run graph algorithms and run complicated queries. And then you can pull that data back out into, let's say, MLlib to train your models. And when we talk about how do I choose between Spark and Neo4j, Spark is great for being scalable, really powerful data pipelining, and it lets you start experimenting. So you can project your data frame into a graph frame and you can say, do I have a graph problem? What would my graph schema look like? I can run simple 1 and 2 hop queries to understand how it's associated with a graph. Once you have that and you understand that, you can pull the right set of data into Neo4j to start building graph solutions. So you have a database where you can persist your data, you can have graph native query and algorithm optimization, and then you can make use of our constantly growing list of graph algorithms and embeddings to answer your questions more powerfully. So stepping back to now you understand how it's done. So cool, I pull my data into Neo4j, I run some algorithms, and then I put it out into my machine learning pipeline. What am I doing here, right? How do I get started and how do I add value? And I really like to frame this as the steps of graph data science. So what I'm going to do for the second half of this talk is walk through steps that you can do to get started and going from left to right, kind of more complicated, advanced, sophisticated. They all build on each other. So we kind of have to start off with, I need a graph to do data science on a graph, right? So the foundation when we talk about graph data science is having a graph that you can query. So for each of these steps, I'm going to walk through an example, a real world example of how you can do something with a graph to add value and learn and improve your models. So step 1, I have a graph, I want to query it. Building on that, Now that I have my graph and I can answer basic questions, I actually have a machine learning pipeline. Let's say I'm training a random forest classifier. I want to use Cypher, our query language, to engineer specific features based on what I know about that data that I can put into my model. Building on that, and you step back and you actually say, I don't want to hand engineer these things. That's when you start using graph algorithms. These are kind of a category of algorithms that tell you about the topology and network structure of your graph. And they fall into different categories, but generally speaking, they're unsupervised learning algorithms that extract key information about your graph. So instead of hand engineering it as a domain expert, you run a graph algorithm and you can put that into your pipeline. The next step, kind of increasing in sophistication, is a graph embedding. And I really like them to think of them as kind of a pivot point between graph algorithms and deep learning or neural networks. So graph embeddings are basically custom trained representations of your graph for the thing you're trying to predict. So a graph embedding is basically a type of graph algorithm, but it's customized to the graph that you're running it on. We'll talk more about all of these later on. And then the last step is what DeepMind and Google Brain were talking about, this graph neural network concept. So instead of pulling my data into a machine learning pipeline, I have a graph as my input. I learn on that graph, and then the output is another graph. And so let's start off with query-based knowledge graph. This is really the simplest first step, great place to get started. If you've seen presentations from Neo4j before, we really like to talk about the lessons learned graph at NASA. This is actually one of the earliest projects that I'm aware of that we still talk about. So in 2012, we worked with NASA to basically create a better way of accessing documents. So what they had is they had, documents from decades of research and history and lessons learned. They had, engineering plans, they had memos, they had white papers. How do you find what you actually need to answer the question that you need to answer for the job you have to do? This is that foundational piece. So they used a combination of topic modeling and things like PageRank and just linking which papers reference which concepts to create a knowledge graph. And once they had that knowledge graph, we have this great example of the uprighters on this capsule. So they needed to build something they hadn't built in several decades. They were able to leverage this graph, query it, and find the information they needed to fix the problem. And it saved them 2 years of work and $1 million of taxpayer funds. So the bottom line here is you need a graph to get started. A knowledge graph allows you to answer the questions that you need to ask very efficiently. And there is value even in the first step. We're not saying there's no value until you're running a neural net. At every step in graph data science, you're empowering yourself to do something you couldn't do before. So cool, I've got my graph. Now I want to start doing some feature engineering. And when we talk about feature engineering, that's basically reshaping your data to add new columns to that tabular data set for predictions. So an example I like to cite here is churn prediction in a telco network. So telecom networks are really easy to represent as graphs. I have kind of a complicated schema here from one of our blog posts where you have, companies calling each other, you have connections, incoming, outgoing, what happened to them. You can kind of also simplify that and just think of, I have different phone numbers that are calling each other. And churn prediction is basically, I have a network, I want to know who's going to leave it next. And I want to be able to predict for the next month who's at risk of leaving so I can devote resources to preventing that. And so research in this space has actually found that simple hand-engineered features are really highly predictive. So these are things like I have my graph and I want to know how many calls or texts has this account made and to whom, and how many of their contacts in this graph at 1 or 2 or 3 hops have churned. And this is from a paper by Khan et al. From 2015. There's another paper that I can cite as well, where they basically took their data, they reshaped it into a graph for feature engineering, and they added graph-based features. Almost all of these were hand engineered. So they looked at the features and figured out which ones were most predictive. And what they found were these simple hand engineered features of what was the in degree and what was the out degree, and what was the in degree during the day and what was the change, how many incoming calls did I have versus my neighbors have, were some of the most predictive features in this model. So this is an example of someone who knew a lot about telco and churn, using the graph that they built from their data and making simple queries to find out, okay, I know that these are important features. I'm going to query it, I'm going to generate this number, and I'm going to add it to my predictive model. So it's really powerful. It's a way of, just like we talked about, knowledge graphs let you answer the questions you should be able to answer. The hand-engineered features are a way of saying, I know this is important, I'm going to leverage the graph to get this information out. If we want to talk about fraud detection, you could cite the example of looking at how many users do I have in 2 hops from this account who've committed fraud. So how do I actually do this? Going back to that Spark framing we talked about, you can merge your data, reshape it into graphs, start exploring it with Cypher queries in Spark. Once you know you have a problem and you figured out what you want to do, move into Neo4j, and then use your queries to interact with that data and export it into your machine learning pipeline. Building on that, we want to start using graph algorithms. So these are the unsupervised category of features. And just going back, reminding everyone what feature engineering is, this is how you combine and process your data to create new features. So you've probably seen by now examples from Game of Thrones. You have your interaction graph. I want to predict who is going to win the Game of Thrones. I could have started off with my tabular data of who's in which house, but then I can start running graph algorithms and adding columns that represent things like influence with PageRank, or relationships with degree centrality, or which communities individuals interact with using something like Louvain. And so I'm just adding columns to my data set. Neo4j has 5 categories of graph features, and coming up on a 6th one shortly. We talk about community detection, which is how you partition your graph into clusters based on which nodes are more tightly connected to each other than other nodes in the graph. So label propagation and Louvain are examples of this. You have centrality and importance algorithms, which determine the importance of distinct nodes in your network. So this is something like PageRank. You have pathfinding and search, which find the optimal paths and routing across your graph. You have similarity, which lets you say how alike are any 2 nodes in my graph based on either their relationships or the nodes they're connected to. You have heuristic link prediction, which is basically I have some rules about whether or not a link should be present, and I want to calculate a probability that 2 unlinked nodes should be linked. And the last category is embeddings, which we'll talk about later. And so for this, we like to use the example of financial crime because different algorithms can answer really different sets of questions. So if I have my transaction graph, I have my account holders, they have various identifiers, they have bank accounts, they make transactions with each other. This is a really naturally graphy problem. Financial institutions already have modeling pipelines and heuristics that they use for this. Graph algorithms just add new data points they can use. So if you're looking at something like first-party fraud, where you want to find out, okay, who is committing fraud by creating fake identifiers, fake authorized users on their accounts? I can look at something like connected components, which will find all of the disjointed subgraphs in my graph that have shared identifiers. I could use something like PageRank if I want to find accounts that are making more transactions or larger transaction volumes than I would expect. If I want to do something like try to find money laundering, where I have account holders who are repeatedly passing money between each other, not in like a simple 1-hop way, but let's say in a 6-hop way, I can use Louvain to identify these fraud rings and then pull that data out. Or let's say I have some account holders that have been labeled as fraudulent, and I want to look at my other account holders and figure out, are they likely to commit fraud too? I can use Jacquard to say, this account has committed fraud. What's the most similar other account in my graph to this account based on who they're interacting with, because maybe I want to investigate them next. Again, just circling back, this is not Neo4j making up uses for Neo4j. There are over 140,000 peer-reviewed publications on this topic in the last 10 years. This is a really hot area of research. It's really useful and it's really powerful. Just circling back to how do I do this? Again, we talk about merging your data, pulling it into Neo4j, running those graph algorithms, and either interacting with those results directly or bringing them into your machine learning pipeline for training. And so in Neo4j, I'm sure you've heard other presentations today where we've talked about we have 45 different algorithms across these 5 classes. I work with the product engineering team where we're working on ensuring that these algorithms scale up to billions of nodes and relationships, terabytes of data. So what we're doing is picking up the highest value and kind of most requested algorithms and remaking those so that they scale to the biggest graphs you can throw at us. So the ones I've highlighted in yellow, the team has already worked on, and what we're doing now is going algorithm by algorithm based on demand and making sure everything scales. So this is something super exciting. Next step, graph embeddings. So I'm going to actually be speaking on this later this afternoon. So I'm going to skim over some of this section. If this sounds exciting, tune in at 1:15. But a graph embedding is just a way that you transform your graph into a vector or set of vectors that describes the topology, connectivity, or attributes of nodes and edges in the graph, right? And you can create different types of embeddings. So you could have a vertex embedding where you're describing the connectivity of every node, and that's how Deep Walk works. A path embedding where you have traversals across your graph, and you want to create an embedding that represents those. Or you can have a whole graph embedding where you want to encode your entire graph into a single vector. And this is really relevant, especially in my background in the chemistry space. So I want to encode a molecule as a graph. Basically, all I'm saying is I want to take some part of my graph, be it a node, a relationship, a path, and I want to represent that as a series of numbers that represent weights that help me tell the difference between individual nodes. And because they're numbers, I can easily put those into a machine learning algorithm. So a cool example of this that I really love to cite is from eBay. They were doing reasoning over a knowledge graph for recommendations, and this is a path-based embedding. So what they had is they had a user interacting with a song, and they wanted to know, well, which song should I recommend to that user next? But that song that the user interacted with, Alice likes the song The Shape of You, is part of a knowledge graph. So there's all of this context around the song. So it's sung by Ed Sheeran. It's a pop song. Ed Sheeran also sang Castle on the Hill, etc., etc. So can I leverage paths across this knowledge graph to make better predictions? And so what they did is they extracted all of the potential paths in that graph, up to 6 hops, between the user and the endpoint or the song they were recommending. And then they used an embedding to condense that to basically a vector of numbers that they could then use to say, well, what vector is most similar to this? So what should I recommend next? And this is really cool because it's a way of taking something very complicated and adding context in a way that's easy to use sort of in a machine learning pipeline. When we talk about doing this in Spark, basically same concept, move your data into Neo4j, write it to your graph to persist, stay tuned for graph embeddings, and then once you have those, bringing those into your machine learning pipeline. The last step, and I've got 1 minute to talk about this, is the graph neural network. And so this is kind of the most sophisticated, most advanced endpoint, which you really don't see in production outside of basically image processing or kind of video recognition. And graph native learning, when we talk about graph neural networks, is a type of deep learning, which just means you're training multi-layer neural nets using gradient descent. So you have an input, hidden layers, and an output layer. Graph native learning, or graph neural networks, are deep learning models that take your graph as an input, perform some kind of computation on that graph, and then return another graph. So this is from the DeepMind paper. You have kind of your standard steps are you have your input graph, you do an edge update, you do a node update, and then you do a global update, and then you make a prediction. A cool example of where this is actually being used is in electron path prediction. So if you represent your molecules as graphs, you can encode those into, you have your molecule, it's a graph, you represent it as a graph. Given 2 molecule graphs and some reagents, what will they form and how will they form it? So you have 2 input graphs and a reagent, and you have a data set of these 2 were combined with this, and you got this output. You train the neural net to say, here's my input graph, here's my output graph, what are the steps in between? And then you can predict not just what 2 reactants will form, but also what the mechanism by which they form it is. And since I'm crunched on time, I'm not going to go a lot into this, but it's pretty cool. And so just stepping back, to where we got started. So we start from building a knowledge graph, hand engineering features, using graph algorithms for features, using graph embeddings to train custom algorithms for your graph and your use case, and then graph neural networks, so you're staying kind of natively in your graph from end to end. If this is exciting, please check out the Graph Algorithms book. Feel free to contact me. I can talk about this all day. And so now just the comprehension check, if people were paying attention, the Hunger Games questions. And let's see. I should keep those up though.
Okay, hi, this is Jennifer. So we do have one question coming in on the Q&A. So asking, are there embedding techniques that work beyond just ones and zeros of the adjacency matrix? In other words, can embeddings typically based on the adjacency matrix that also embed node and edge labels? Don't think things like node to vec do.
There are embeddings that exist to take into account more than the simple adjacency matrix. So if you think about something like GraphSage, those are not currently implemented in Neo4j, but they exist, and they're like a really active and exciting area of research. So the kind of field is moving towards more sophisticated techniques where you can consider more than just the, this is connected to this, where you can say something like using PyTorch's Big Graph or a Rescale or something like that. You can say, I actually want to look at different node labels, or GraphSage lets you look at attributes. So research is ongoing in this area. It's a matter of how do you take that into production.
Someone asked about machine learning examples to share.
Specifically about graph embeddings, or just in general?
Looks like graph ML examples.
So this will be posted to YouTube afterwards. Every example that we kind of walked through in here is an example where graphs were being used for machine learning. If there's a specific use case you're curious about, happy to talk more. If you're kind of more interested in a specific category or whatever, you can type it into the Q&A box.
Okay, one on if your data is not originally in the graph, do you see any reason for bringing the data to graph and then using graph embeddings to model it as vectors?
So there's a couple questions here. So one is, if your data is not in a graph, should you bring it into a graph? And the answer is, if your data is possible to move into a graph and the thing you're trying to predict can benefit from a graph-based feature, then it would be beneficial to move into a graph, right? So if I'm talking about my Telco-churn prediction example, I have my rows and columns, but I have a suspicion that something like how many people 2 hops away in the graph tells me if someone is going to leave or not. Then I would want to say, okay, I'm going to move this into a graph. When you ask about should I use a graph embedding, I think maybe the confusion is I'm saying, well, a graph embedding flattens your graph into a vector. But what a graph embedding does is it uses the relationships in your graph and the topology of that graph to learn weights for that vector. So that vector actually represents the neighborhood around that node and the structure of your graph as something that's easy to put back into kind of that tabular data format.
And someone asked about using R with Neo4j to do a range of data science.
So I believe there is an R connector that was put out by the labs team, like an experimental R driver, so you could connect directly. The other thing you can do is you can run things in Neo4j, export it as a CSV, and then import it into R. So you can either connect via the R driver, or it's sort of more hand engineered. I want to use, I want to export to a flat file and then pull it in.
Okay, probably one more question and then probably out of time. So someone asks, how big are the graphs? number of nodes and number of edges for these pipelines, and do you need distributed execution for these? Can you say something about performance scaling for these algorithms?
So for our algorithms, the largest production use cases I've seen of algorithms has been on a multi-terabyte graph with I think the largest I've seen is like 9 billion nodes and 20 billion edges. So our algorithms scale really well, but you need to have a sufficiently beefy machine. So they can run concurrently, they're optimized, they run on an internal data structure that's customized for graph algorithms. They scale really well, and they actually don't require distributed processing. So what's really interesting is some graph algorithms just don't distribute very well. So if you look at Spark, you'll see a handful of graph algorithms, but not as many. And that's because not all of them can be distributed. So what Neo4j lets you do is run over a giant graph and run those algorithms that don't distribute well.
Okay, that's probably where we have to stop for today. We will try to paste a couple more things into the chat. I'll send a couple of links out as well to answer some things. For those of you interested in learning more about this topic, there is a lightning talk after this on leveraging graph algorithms and visualizations. There's also one by Amy Hodler and Mark Needham, a full-length session on community detection and recommendations using graph algorithms, and more, of course, another one from Alicia coming up after that on graph embeddings. So if you're curious more about this topic, there's plenty more material coming up, and hopefully we'll answer all your questions throughout.
And thank you everyone for joining. This was fun.